Carbon dioxide is the most common greenhouse gas produced in industry. Today, we'll discuss some options for mitigating the emission of carbon dioxide when its production is unavoidable. In our pulp mill, carbon dioxide is produced in the multi-fuel boiler, which combusts biogenic waste of the pulp-making process, the black liquor boiler, which recovers both chemical and energy from the pulp and cooking residues, and at the lime kiln, which is also part of the chemical recovery process. Our pulp mill is almost entirely energy independent. It exports electricity, and almost all of its produced carbon dioxide is biogenic. Therefore, it may not be desirable to replace the existing energy production. Furthermore, the black liquor boiler and the lime kiln produce carbon dioxide for process reactions other than energy generation, which cannot be avoided by decarbonizing just the energy supply. But just because a process produces carbon dioxide does not mean it has to emit carbon dioxide. In principle, carbon capture is the process of separating carbon dioxide from a mixed gas stream, such as from the flue gases from a multi-fuel boiler or lime kiln. Today, we will introduce two types of carbon capture: post-combustion capture, which functions similarly to the diagram shown here, and oxy-fuel combustion capture, which uses a different order of operations to achieve a similar effect. Post-combustion capture separates the carbon dioxide from a gas stream, such as the flue gases from a lime kiln. First, the gas is cleaned, removing particulate matter, sulfur, and nitrogen oxides. This gas cleaning process is often required to meet environmental regulations, and so may be pre-existing in many industrial processes. This step also makes CO2 separation easier by removing contaminants that can interfere with separation or damage equipment or chemicals. The clean gas is then sent to a CO2 capture unit, which can use, for example, a chemical absorbent, a swing absorption process, or a membrane to separate the carbon dioxide from the rest of the gas stream. After separation, the clean flue gas, which now only contains a small amount of carbon dioxide, can be released to the atmosphere. Depending on the technology used, the carbon dioxide may need to be released from its absorbent in a so-called stripping process, which also allows the absorbent to be reused for capture again. Post-combustion capture has the advantage that it can be tacked on to an existing industrial process, as it does not require altering the CO2 emitting process. We should note that, in general, the higher the concentration of carbon dioxide, the less energy needed. This is why it will always be more efficient to capture CO2 before it is released in the atmosphere than attempt to remove it from the atmosphere later. Some processes, such as the fermentation of ethanol, already produce a pure stream of CO2, and therefore capturing carbon dioxide may only require gas cleaning to remove any contaminants and/or condensation to remove residual water. But it is also possible to modify some CO2 producing processes, such as combustion, to produce a pure CO2 stream. This is called oxy-fuel combustion capture. Oxy-fuel combustion allows the carbon to react in a pure oxygen environment instead of ambient air, generating a gas stream that is almost pure carbon dioxide. Oxy-fuel combustion capture requires retrofitting the combustion environment to be airtight, adding an air separation unit to provide oxygen, and potentially adjusting the process parameters to compensate for this all-oxygen environment. In this capture process, the main energy demand comes not from the CO2 separation, but from the separation of oxygen from air. However, capturing carbon dioxide is only the first step. We must always consider what happens to the carbon dioxide after it is captured. Typically, this will involve compressing the carbon dioxide, which allows it to be transported by pipeline, ship, or truck to where it can either be reused or stored. Captured CO2 can be stirred permanently out of the atmosphere, for example, by injecting into an exhausted oil or gas well, saline aquifer, or other geologic formation, where gas can be safely trapped. This is called carbon capture and storage, or CCS for short, and substantially reduce the amount of carbon dioxide entering the atmosphere. The captured carbon dioxide can also be used as an input into another process, This is called CCU, carbon capture and utilization. For some processes, such as beverage carbonation or greenhouse agriculture, the carbon dioxide is used directly. The carbon dioxide can also be converted into carbon monoxide via electrolysis, which is energy intensive but allows the carbon dioxide to then be used as an input to create other chemicals. However, most forms of reuse result in the carbon dioxide being re-released into the atmosphere. Thus, whether or not it mitigates greenhouse gas emissions is dependent on whether the reuse of carbon dioxide sufficiently reduces carbon dioxide emissions by displacing the use of other types of carbon. A few types of carbon dioxide reuse can result in long-term storage, such as mineralizing the carbon dioxide into concrete or silicates. The use of carbon dioxide in enhanced oil recovery does also store CO2 underground, but the CO2 emitted from the additional oil recovered typically leads to more carbon dioxide being emitted than was stored. To end, let's visualize the impact of carbon capture on the carbon balance of a system. Without carbon capture, carbon dioxide is released into the atmosphere. If that carbon dioxide is fossil-based, then our system is carbon positive. If that carbon dioxide comes from a biogenic source, such as in our pulp mill, the carbon balance is still positive but less so, as the carbon dioxide emitted into the atmosphere by biomass was originally removed from the atmosphere via photosynthesis. However, the system of producing and transporting biomass is almost never fossil-free, and therefore bio-based systems are almost always still CO2 positive. The effect that carbon capture has on the carbon balance depends on where the carbon dioxide ends up. If the carbon dioxide is reused and re-released, then our system is still carbon positive. If the carbon dioxide is fossil-based and that carbon dioxide is stored permanently, the system can be less or even minimally carbon positive. It cannot be carbon neutral, as there will always be losses. For carbon capture to result in carbon negativity or carbon neutrality or even carbon negativity, the carbon dioxide captured must be atmospheric in origin, such as from biomass, and must be stored permanently after capture. Understanding the impact of carbon capture on the carbon balance of our pulp mill or any system requires looking not only what happens at the mill, but also in other parts of our system, such as what happens to the carbon dioxide after it leaves the mill, and how the energy produced for carbon capture is produced. This system perspective is what I'll be talking about when you see me next week for Module 2.2 on life cycle assessment. Bye for now.